It exists between 0 and 1. A specific value, exact, real, formally defined, not approximately known, not currently unknown, not awaiting better mathematics, permanently, structurally, provably unknowable. This is not a philosophical position. It is what the proof says. The proof has been checked. The number exists. The number cannot be known. Both of these are true simultaneously, and neither cancels the other, and this has been the case since the moment the number was defined, and will remain the case for as long as mathematics exists. A universal Turing machine, a program chosen at random. The probability that it holds, that is omega, not a metaphor, not an approximation, not a limit approached from below. The exact probability, summed across all possible programs, each weighted by the probability of being chosen at random. Each either halting or running forever is a real number. It has a decimal expansion. Each digit is either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. The digits exist. They're not random in the casual sense. They're not noise. They're not arbitrary. They are the precise output of a specific mathematical definition applied without ambiguity. The number is defined. The number is real. The number is between 0 and 1. And no formal system, no axiom system, no proof procedure, no mathematical framework powerful enough to define the number in the first place can determine more than finitely many of its digits. Not more digits with more effort, not more digits with stronger axioms, finitely many. Fixed, a ceiling that does not move regardless of what is added to the system during the asking. The number is there. The digits are there. The system cannot reach them. Why? Turing, 1936. A machine that reads symbols, writes symbols, moves left or right, changes state, halts or runs forever. The question: given a description of any machine and any input, does the machine hold? The proof that no machine can answer this. Assume a machine H exists that solves the halting problem. Build a machine D that takes any machine M as input, runs H to ask whether M holds on its own description, and then does the opposite. Holds if H says M runs forever if H says M holds. Ask D what it does when given its own description. If D holds, H said D runs forever, but D holds when H says it runs forever. Contradiction. If D runs forever, H said D holds, but D runs forever when H says it holds. Contradiction. H cannot exist. The halting problem is undecidable, not difficult, not currently unsolved, not requiring more computing power, undecidable. No machine, no formal system, no procedure, no algorithm can determine for all machines whether they hold. Omega is the halting problem compressed into a single number. To know the nth digit of omega is to know for infinitely many programs whether they hold. To know all the digits of omega is to solve the halting problem completely. The halting problem cannot be solved. Therefore, omega cannot be known. Not more of it, not eventually, not with stronger axioms. Because stronger axioms are themselves programs running on machines whose halting behavior is part of what omega encodes. The system trying to know omega is inside omega. The number contains the question of whether the system asking about it will ever stop. What this does to mathematics, not to computation, to mathematics. Gödel showed that any consistent formal system strong enough to encode arithmetic is incomplete. There are true statements it cannot prove. Heiting showed something stronger. For any consistent formal system F, there exists a constant, the complexity threshold of F, such that F cannot prove, for any specific program, that the program's Kolmogorov complexity exceeds that threshold. In other words, there is a ceiling on the complexity of what any formal system can prove exists. Anything above the ceiling, and almost everything is above the ceiling, is invisible to the system. Not hard to see, invisible. The system cannot prove it is there. Almost all real numbers are like omega. Almost all real numbers are incompressible. Their shortest description is themselves. Almost all real numbers cannot be computed, cannot be approximated arbitrarily closely by any algorithm, cannot be reached by any formal procedure. The real numbers that mathematics can actually work with, the rationals, the algebraics, the computable reals, the numbers with names, are a vanishingly small fraction of the full real line. Mathematics is a vanishingly small fraction of what exists mathematically. The part of mathematics that mathematics can do is an infinitely thin sliver of the mathematics that is there. Omega is not an exotic exception. Omega is the typical case. The numbers with names, the square root of 2, are the exceptions. The permanent unknowables are almost everything. The physical universe has a finite information content, the Bekenstein bound. The maximum information encodable in any physical region is proportional to the surface area of that region. Finite region, finite information. The universe is a finite computation. A finite computation has a Kolmogorov complexity, a shortest program that produces it. That program exists. It is a finite string of symbols. It is running on something. We do not know what. We cannot determine it from inside the computation. Because determining it from inside would require solving the halting problem for the computation we are part of. Which is exactly what omega encodes. And omega cannot be known. The fundamental equation of quantum gravity, h psi equals 0, describes the quantum state of the universe as a whole. It contains no time variable. The universe at the most fundamental level is static, a frozen wave function If the universe is a computation, and the Bekenstein bound suggests it is, then asking whether that computation holds is asking whether the time ends. And the answer is encoded in omega, and omega cannot be known.
The formal system that defined omega is inside omega. The proof that omega cannot be known is a computation. That computation either holds or it doesn't. Its holding behavior is one of the things omega encodes. The proof of the unknowability of omega is itself subject to the unknowability of omega. Not because the proof is wrong, but because the proof is a machine whose behavior is part of what cannot be known. This argument, everything just stated, is a formal system. It is expressive enough to define omega. Therefore, it is subject to Huygens incompleteness theorem. There is a ceiling on the complexity of what this argument can prove. Everything above this ceiling is invisible to the argument. The argument cannot see its own ceiling. No argument can. Omega does not describe a limit somewhere out at the edge of knowledge. Omega describes the structure of knowledge itself. The fact that any system powerful enough to ask precise questions about what exists is guaranteed to be blind to almost all of what exists. The precision is the blindness. The expressiveness is the limit. The power of the system is exactly what generates the permanent shadow the system cannot enter. Omega exists. Omega is between 0 and 1. Omega has digits. The digits are specific. None of this is in question. The digits cannot be known past a finite point. The finite point is determined by the formal system doing the asking. Different formal systems have different finite points. No formal system has an infinite point. The digits continue past every finite point that any formal system can ever reach. They are there, past the reach of every system that will ever exist. Not because they are hidden, not because the mathematics is incomplete in a way that more axioms would fix. Because the structure of formal systems, the very structure that makes a formal system powerful enough to define omega, guarantees that the digits exceed what the system can see. The number is there. The canvas cannot hold it. This cannot be finished.